Hello, this is Brother Kumar from the Math Department. This is a continuation of the videos dealing with inference for two means independent samples. So now what I'm going to go through is the answers to the problem that what we talked about at the end of part one. This is the World Cup problem. Now the question here is, let's go through the 6 steps. The first one is to define the known alternative hypotheses, the first step. So how I defined it is that the two population means are equal to each other. So mu1 is equal to mu2, or the population mean of group 1 is equal to the population mean of group 2. The alternative, now I have it here as less than. Now here's it's kind of a twist here because it asks here the mean number of cardiovascular events is greater than during the war, or greater during the World Cup than during the control period. But then I said let group 1 be the control period and let group 2 represent days during the World Cup. So because of how it's worded and how I wrote it here, now it's also written in the textbook, since group 1 is a control group, I made that here, and since we're looking to see if group 2 is greater than group 1, I have a less than symbol here. So you can switch it around if you want to, or you say mu2 is greater than mu1, but I wrote it like this, okay? You could do it either way so long as you keep track of it, okay? So steps 2 through 4 is our test statistic degrees of freedom and our p-value. Now where I get those results, I get them from, I'm going to go to my SPSS output, and I'm going to grab them here. So we're going to use with this table here, we'll use the equal variance not assumed, the bottom row, since it's always right. We're going to get a test statistic here, degrees of freedom here, and a p-value. Since we're doing a one-sided test, if you're using SPSS, we would take this number divided by 2. But since it's a number that's close to 0, now I say close to 0 because it's not exactly 0, okay? It's 3 decimal places to the right, it shows 0, but there's other numbers. It's never going to be 0, but in this case it's awfully close to 0. So that's why I have written up here close to 0. So then the next step is, do we reject the null hypotheses? Well, we compare a p-value to our level of significance. And since our p-value is less than the level of significance, we reject the null hypothesis. So then we have sufficient evidence to say that there are fewer heart attacks outside of World Cup competition time frame than during the World Cup competition. Okay. So now let's go talk about confidence intervals. Confidence intervals, let's review some confidence intervals here. Here's the very first confidence interval that you saw where it was one mean, and it was where we knew the population standard deviation. So we took a sample mean plus or minus a margin of error where we used the z-distribution to get a critical value, and we have the population standard deviation. However, we realized that it wasn't how realistic is the population standard deviation known. Well, it's not really realistic, so we used this confidence interval where we used the one mean sigma unknown, so we used the t-distribution to get a critical value, and then we used the sample standard deviation to estimate our population standard deviation. So this is the second confidence interval that you guys ever saw. However, we used SPSS or Excel to calculate our confidence interval, okay? And then it's the same with this confidence interval where we dealt with matched pairs where we have a sample mean difference here, plus or minus a margin of error where we take a critical value from our t-distribution times the sample standard deviation of the difference divided by the square root of our sample size, which n is the number of pairs, or the number of pairs in our sample, okay? And so we take a point estimate plus or minus a margin of error. And we would also use Excel or SPSS to calculate our confidence interval. So the confidence interval today, here's the formula for it. It's not in the textbook, but it's basically, I point this out to show you that it's still a point estimate plus or minus a margin of error. Our point estimate is the sample means, the two sample means and the difference between the two sample means. And then we add and subtract a margin of error where we still use the t-distribution to get our critical value. And then we also have standard deviations, the standard deviations squared here, which are called variances, but the standard deviations as well as the sample sizes. To get everything combined would be our margin of error. This is what you see down here. Okay. This is also calculated. You will be calculating this using SPSS or Excel, depending on your class. Okay. So let's go back to the first example that we covered dealing with hypothesis tests. Now we're going to look at this in terms of confidence intervals. So if you remember, there were two groups of reading practices for children. One is a developmental or behavioral problems group, or group 1, and we compared that to a general population who do not have developmental problems, or problems. So one of the factors the researchers considered was the number of nights each week the children participate in reading. So down to this sentence here, calculate and interpret a 95% confidence interval for the mean difference in the number of nights each week that the children participate in reading in the home between the two groups. Now this is the confidence interval I got here. If you go to this, to the output here, I'm going to go back to the SPSS output I have. This is where I get my confidence interval. I use the bottom row and I grab these two numbers. So the lower bound is negative 0.149, the upper bound is positive 0.987. So what we say is that we are 95% confident that the mean difference is between negative 0.149 and 0.987. So is there a difference? Can we tell if there's a difference between the two groups doing the 95% confidence interval? Well, it looks like since 0 is in the confidence interval, we cannot tell if there's a difference between the two means. Because if we're taking group 1 minus group 2, it looks like a lean towards group 2. However, we could also get a mean difference based on our results that could be negative as well too. We're saying with 95% confidence that the mean difference is between these two numbers, or the difference between the two means between these two numbers. So it can either be positive or negative, and ultimately, since 0 is in the confidence interval, we cannot tell a difference. Let's go through the second example using the World Cup data. So this is the same data that we used. Now we're going before using the hypothesis test. Now we're going to deal with it with the confidence interval. So going down to here, let group 1 be days in the control period, and let group 2 represent the days during the World Cup. Calculate and interpret a 99% confidence interval of the mean difference in the number of cardiovascular events between the two groups. Now I got a result of negative 7.771 and negative 2.141. Where I got that result, let me go down to my second table here, is this number right here. Okay, so when we go back, how we interpret that is that we say that we are 99% confident that the mean difference, or the difference between the two means, is between negative 7.771 and negative 2.141. Okay, now in this case, can we tell if there's a difference based on our confidence interval? The answer is yes. 0 is, I should say, not in the confidence interval. It says is in the confidence interval, but it's not in the confidence interval. I'll just type that in here, is not in the confidence interval. So there appears to be a difference between the two means, okay? And so 0 is the magic number when we're looking at matched pairs and independent samples to see whether or not there is a difference, okay? Now lastly, let's talk about checking requirements, okay? So before doing an independent samples t-test, the requirements to check to do independent samples is, first of all, the samples need to come from both simple random samples. Samples are independent, unlike dependent, they're independent. And the distribution of sample means is normally distributed for each group, okay? For each group, check that either the data are normally distributed, so use QQ plots, or check to see if the sample size is large. Now, on top of that, the descriptive statistics that you can use for this data is that you can find the sample mean and standard deviation for both groups. That would be the numerical descriptive statistics. And in a graphs, you can do the histograms or box plots for both groups. So here, if I'm going to go to my output again, if you follow along with me here, here's an example of where we can get the histograms of both groups, okay? This is the first problem where you have the developmental and behavioral problems, and this is the output in terms of the number of times that they read, nights per week that they read at home. And then this is for the developmental group, and this is the children without developmental problems, okay? We can also get, if we go further down, we can also get means and standard deviations here. Here's a mean, two means from the two groups, and the standard deviations. You can find something similar in Excel. And then these are the QQ plots here, okay? So this is a QQ plot for the developmental group, and this is the QQ plot for the general group. And it looks like that the data appear to be normally distributed, okay? And this is the box plots down here. Now, if I look at this here, the sample sizes are pretty high anyways. So we could probably assume, given these sample sizes are large, that the distribution of sample means is normal, okay? And that is it for the lesson. The lesson dealing with inference for two means independent samples. If you have any questions, please talk to your instructor or to one of your TAs.